This will be our first CMPS 211 solving session, one of many hopefully to come. I'm Abbas Naeem, and just for reference, when I did the final for the CMPS 211 course, the average in our section was in the 40s, the other section was like 30s, something like that, and I got 100. And it's not really to brag. This course is A+able. It's unlike some people are saying in the last 2 semesters, especially, that it's a really tough course. And actually, in the spring, like only 2 people maybe got an A+, and that's really something that shouldn't happen because this course is not as tough and as hard as people may make it to be. It's really important in this course to actually think about the questions, not just take the solutions quickly, especially maybe in the proofs for harder questions. And hopefully we will be looking at the harder questions in the next solving session. Okay, so first let's start with this exercise. Exercise 1. Okay, so 1 over y equals 5. Is this a proposition or not? Actually, in this first one, there's a bit more to me than meets the eye. Some people might directly say that it's a proposition. Some people might directly say that it's not. Okay, so let's see why. First, what is a proposition? A proposition is something that can hold a truth value. What does this mean? It means that I could assign to it true or false. I could say that, okay, this sentence is true, this sentence is false. Okay, so some people might say that 1 over y equals 5 is equivalent to saying that for some real number y, maybe y is equal to 1 over 5, or like 1 over y equals to 5, as they said. And actually, this is a proposition. So are they equivalent? Think about it for a minute. The answer is no, they are not equivalent. Why are they not equivalent? Okay, so 1 over y isn't actually saying anything, because I cannot assign to 1 over y equals 5 a truth value without knowing what y is. What is y? So like if you say that for y equals 1, 1 over y equals 5, okay, so I could say that this is a proposition. Or if you say like for some y, 1 over y equals 5, or for every y, 1 over y equals 5, these are all propositions. But without saying what y is, I can't really say that this is true or false. So what is y? Is it a variable? Is it something? What is y? Okay, so this one is not a proposition. What's your name is also not a proposition. Why is that? No, because I couldn't assign to it a true or truth or false value. I spent all my money on books. Think about it. Yes, it is a proposition. Why? Because I could say yes, I spent all my money on books. No, I didn't spend all my money on books. Do not pass. Just go. Is this a proposition? The answer is no, because it's a command. I couldn't say that this is true or this is false. NAND gates are the primitive components of CPUs. Okay, so let's see. Assume that I assume that most of you are not experts in this field. But if you were expert in this field, you'd know that this sentence is actually true. Okay, but does that mean that it's a proposition? Because we already know that it's true. If you look at the one before, that was clearly a proposition. When we said, I spent all my money on books. Okay, so you could be lying. This could be false. It could be, and it could be saying the truth. It could be true. So actually, from this info, I don't know if it's true or false. All I know that is I can assign this value. I can say that, okay, it's true, or okay, it's false. But what about this? I already know that it's true. Does this make it not a proposition? Think about it. And actually, no, it is a proposition. It remains a proposition even if the truth value is known. The idea is, the definition is, a proposition is something that could be assigned the value of true or false, and this could be assigned the value of true or false. Okay, so as you see, not a proposition, but a proposition. It's a proposition, the box one, and then the command is not a proposition, and then it is a proposition true. Okay, so this question is really easy. Actually, a lot of the questions that we will be going over today maybe are pretty easy. The next problem set will be actually a bit more challenging. This one is to get you to know all the topics. At least for me, maybe I didn't go over the slides when I was studying. I don't even know if I was taking notes. Mostly for this course, I just solved questions. And this might be the better approach, because you'd know all the rules maybe through solving. So let's start with this next question. Okay, So determine whether these biconditionals are true or false. Okay, so first, just a very quick introduction to biconditionals. I'm already sure that you've seen them in class, but I will just point out a few things that are maybe nice to know. When I say that P, if and only if Q. Okay, so in class you've already been taught that if both are true or both are false, this is true. So it's only true if they both have, if they both hold the same truth value. Maybe the brighter among you have noticed also that it is equivalent to saying that not P XOR Q. Why is that? Because XOR is only true when they have different truth value, and the biconditional is only true when they have the same have the same truth value. Now, just a very quick note that's nice to know. Why is biconditional equivalent to if and only if? Also, you've hopefully been taught in class. I don't know if they are saying this in class, but the biconditional is equivalent to P implies Q and Q implies P. Okay, so how is this equivalent to if and only if? When I say that P implies Q, what does this mean? This means that if P happens, then Q happens. You could think, okay, so P causes Q. Okay, but this doesn't necessarily mean that the only thing that causes Q is P. Maybe also R implies Q. Okay, but we also know that Q implies P. Okay, so what is this saying? This saying that if P happened, then Q happened. Okay, and if Q happened, then P happened. This is the same as saying that the only thing that causes P, or sorry, the only thing that causes Q is P. Why is that? And the same holds for P, of course, but because I started saying P implies Q. Why is that? Because this sentence, this proposition, is saying that if Q happened, then P happened. So a prerequisite maybe for Q to happen is P happening. So if Q, then P. And also if P, then Q. So also if P happened, then Q happened. So nothing else could cause Q. Because if something else could cause Q other than P, this wouldn't hold, that Q implies P. Okay, so it's not very necessary to understand the last thing that I said, but it was just nice to think about it. Okay, now, so determine whether these biconditionals are true or false. So this is true. We know that 4 times 2 is 14. And 3 over 0 is undefined, so it is true. So the whole sentence is true. This is false. And if Michael Jackson, I believe this is also false. So Michael Jackson is dead, and 2 plus 2 equals 4, not 5. So this is also true. And you could apply the same logic for the next few ones. It's not very complicated. So now, exercise 3, truth tables. Truth tables are very easy. Hopefully, you'll get full grades on them in the exam. Just do a few examples, and it really gets very repetitive. It's not that hard. Just do a few examples, and you will ace it, I'm sure. It's very, very, very repetitive, and you will get bored from it. Okay, so I'll only be doing C because it looks interesting, and because, as I said, it gets very repetitive. Okay, so first we have to identify how many variables we have. Let me change the color. Okay, so first we need to identify how many variables we have. So we only have P and Q. You only have P and Q. Okay, so if I know that I have 2 variables, how many combinations, how many different scenarios, let's say, do I have? Because I want to evaluate the truth value at every single point. We could think about this maybe as, okay, so as events. Event 1, event 2, event 3. Okay, so let's say I have 4 variables. I would have 4 events. Each event could be 1 or 0. So this, let's say this is P, Q, R, and T. So P could be true or false, Q could be true or false, same goes for R, same goes for T. Okay, so how many different scenarios do I have? How many different combinations do I have of PQ being true and Q being false, maybe, and R being true? Okay, so how many scenarios of this kind do I have? For each variable has two possibilities. It could be either true or false. So P could be either true or false. For the scenario that P is true, Q could be true or false, and for the scenario that P is false, Q could be true or false. So the same. So 2 times 2 times 2 times 2. You'll notice that we have 2 power 4 possible combinations. What does that mean? That means that when I'm constructing a truth table, the number of rows should be 2 power number of propositions. So now I have 2 propositions. I will have to make 4 rows. Okay, so PQ. So true, 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 false, false, true, and false, false, maybe. Okay, so just start by putting each one of these smaller components. Okay, so we have P if and only if Q, and we also have P XOR Q, and finally we have the entire thing. Okay, so if they are both true, we know that this is true and this is false. Notice that they will be always currently, without doing anything else. If someone just looks at this is the opposite of this. So this or this will always be true, because always one of them will be true. Because if this is true, this is false. If this is false, if this is true, sorry, this is false. So there's always only one of them that will be true. Notice now this will be false, this will be true, and then this will also be false. This will be true, and this will be true. This will be false. The or between them will always be true. Okay, so let's see it. It's always true. Okay. This was a bit nice. Let's start now with this one. Okay, so we have the following positions. This is one of the types of questions that people always find hard, and it is genuinely, like, they could make it pretty hard, especially maybe in the next solving session. I will bring you the question that was maybe in our quiz 1 or quiz 2. I don't really remember, but there was a nice question on these in the book. There was a nice question on these. I don't really remember it now, but it's mostly wordplay, and hopefully if you solve enough of them, you'll be ready to ace it. So let's see. P is I'm busy, Q is I'm hungry, R is I will order takeout. Okay, so write the following statements in terms of P, Q, and R. Okay, so the first one says that if I'm hungry and busy, I will order takeout. This one is pretty easy. Think about it as always. But let's see. What does being hungry mean? Hungry means that Q happened. Okay. طيب. And busy. So if I am hungry and busy, then I will order takeout, then R. Okay, so you can think about this. If I am hungry and busy, so that means that what does imply that I took takeout? What causes me to get takeout is being both Q and P. So the only time that R, or maybe the only thing that I know to cause R right now, is this being true and this being true. So if both of these are true, then R will happen. So this is the first one. I am not hungry and I am not busy. Same thing. Not Q, so I am not hungry and I am not busy. Okay, same logic as before. I am not hungry and I am not busy. You could think about these questions that the sentence itself that's being said is true. So how would I place the variables in an equation such that this equation will evaluate to true, and such that it is only true when these variables are true, maybe. Actually, not it's only true when these variables are true. but like it corresponds to these variables being true, if that really makes sense. I will order takeout only if I am busy. Okay, so this one is actually a bit trickier. And the reason is that we have the word only. Okay, so I will order takeout only if I am busy. Okay, so let's think about this for a minute. What people would do mistakenly, that way they will say, okay, so I will order takeout if I am busy. So some people would say, okay, then if I'm busy, I will order takeout. This is not true. Why? Because this is saying that being busy will cause me to order takeout, which is true, but it's only half true. Why? Because, okay, so I know that if I'm busy, I will order takeout. That doesn't mean that if I'm hungry, I won't order takeout. We want a proposition that says, if I'm hungry, I won't order takeout. If anything else happens in the world, I will never be ordering takeout except if I was busy. If I was busy, I will order takeout. To achieve this, you would have to say, ordering takeout means that I was busy. Why is that? Because when I say that ordering takeout implies that I am busy, then always when I am ordering takeout, then I am busy. Always when I'm ordering takeout, then I am busy. Okay. And this is actually why the biconditional is if and only if. Because if ordering takeout means that I'm busy, then always, if I'm busy, I'm ordering takeout. There's no way that something else would cause me to order takeout alone. And then when I say that P implies R, what I'm saying is that I don't really need anything else other than being busy. Because if P and Q implies R, then this could hold. But if I say, so what is this saying? That if I'm hungry and busy, I will order takeout. Okay. And if this is the only case that ordering takeout works, actually happens, then R also implies P. Because always when I'm ordering takeout, I'm busy. But when I say that P implies R and R implies P, what I'm actually saying is the ordering takeout is pretty much equivalent to being busy. And there's nothing else. Being busy doesn't really need anything else to make me order takeout. Ordering takeout and being busy are just equivalent. I hope that made sense. Okay, so here they made a mistake. It should have been R implies P. It's a mistake on their side. Okay, so I will order takeout if and only if I am hungry and busy. This one is similar to ones that we have seen before. If and only if, always it's a biconditional, always. So I will order takeout if and only if I am hungry and busy. I would have to both be hungry and busy. Okay, so now for quantifiers. Okay, so if you completed all program requirements, then you're graduating this summer. This one is easy. Always with these types of questions, maybe you have to define a few things. So let's just define a few things first. Let's make P, you complete all requirements, and so P, you complete all requirements, and Q, you graduate this summer. So then, always when you have an if is always an implication. So what does imply what here? P implies Q. Because if you complete all your requirements, you will be graduating this summer, and this is right. Okay, so now the difference between a real number and itself is 0. I really advise you to pause the video to think about this by yourself, and then look at the solution, or maybe if you weren't able to really solve it, to follow along. And see how we usually think about maybe these questions. Okay, so first let's see what can I define in this question. So the only thing maybe that I can see that I can define here is the difference between a real number and itself is 0. So let's define dxy to be x minus y is equal to 0. Then very simply I could say that for every x, where x is a real number, dxx, so the difference between x and itself is 0. Okay, so this is actually true. There are nicer ways. Okay, so it depends on what you define to be nice. maybe there are more interesting ways to say it. Although this would be better for the exam. It's simpler. It's really clear. But just for like curiosity's sake, let's see how can we define it other ways, because you could get maybe in the exam. Uh, you could maybe get in the exam a proposition or something of this kind, and you'd have to put it into words. For that, this will be very useful. The thing that I will show you right now. Okay, so how could I say this in a different way? I could have said that for every x, so for every number x, for every number y, the difference between x and so like the difference between x and y being 0 implies that x is equal to y. So the only way that x minus y is equal to 0 is x being equal to y. This is very simple algebra. So if x minus y equals 0, then x equals equal to y. And it's very important to understand also this. So what does it mean when I say for every x, for every y? Is this equivalent to saying for every y, for every x? Let's think about this. When I say for every x, for every y, what am I saying? Okay, so let's say that these are the values of x. So for every x, I'm going over the values of y. So these are the values of y, these are the values of x. While here, I'm saying something completely different. I'm saying for every y, and then I'm saying for every x. So these are the values of x, these are the values of y. Maybe in this statement that we had just written, it wouldn't have made a difference. Of course, it would have made a difference, but in other sentences, it might. Okay, so let's see. So this is the first simple one that we wrote, and this is the second one that I showed you. This also there's this third way, but really for the exam, if you were given this question, just write this one. Okay, someone in class has an Instagram account but does not follow anyone from class. Okay, so first saying someone directly for some x. For someone in class, where x is someone in class, يعني. Where x is a student in class. Someone in class has an Instagram account but does not follow anyone from the class. So someone in class, okay, so let's define ix as having Instagram account and fxy as x follows y. Okay, so someone in class, for some person in class, for everyone in class other than x, then not, okay, so x and not fxy. So ix and not fxy. What is this really saying? This is saying that someone in class, if you go over everyone else in class, you will find that this statement is true. For everyone in class relative to this person, so it's like this, where this is x and this is everyone in class. And keep in mind that this y also includes x, because x is someone in class. Why didn't I say then that x not equal to y and kaza and kaza? Why didn't I say that? Because if he doesn't follow anyone in class, he doesn't follow himself also. And so it doesn't really make any sense. It doesn't really change anything, maybe. So I don't think that it's necessary to put it. So yes, so someone in class, if I go over everyone else in class, I will find that this person X has an Instagram account, but they don't really follow this Y, and this will hold for everyone. Then he doesn't follow anyone in class. One of the following pairs of statements logically equivalent, show your work, do not use truth tables. For these types of questions, showing that two statements are logically equivalent, these types of questions are really not hard, hopefully. But the thing is that they might take a bit of time, especially if you're not trained well enough to solve them. So just solve a lot of them. It's really not something that's related to understanding rather than just brute force, just solving a lot of questions when it comes to this type of question. Okay, so let's do A. I won't be doing all of them because just doesn't make any sense for me to do all of them. It's really a very, very repetitive process. Actually, I do B because now I've noticed that A is wrong. Why is A wrong? Notice the first one, they didn't solve the same one. And in the second one, they did Q and R, why it's Q implies R. So it's not the same thing, so I'll just do B. Okay, so P and Q. P and Q implies R or S. Okay. And P implies not Q. P implies not Q or S or S. Okay. Okay, so P and Q implies R or S. Sorry for the handwriting. Also, you want to have noticed that these types of questions can be solved using truth tables, but that would be really unpractical, especially when you have more variables. Like, look here, we have 4 variables, and the number of rows grows exponentially. We would have to use 2 power 4 rows. That's just a lot of rows, a lot of writing. Really doesn't need that much. You'll see that the solution is very small. It wouldn't take us very long. So we have P and Q. We will treat this as its own entity and look at the implies. We know that if P implies Q, then not P or Q. Okay, so we will treat the first one as its own entity. We'll say that not the first one or S. So not the first one or the second one. The first one, we will take the not inside. This will become not P or not Q. And of course, do not forget to, in the exam, to write here the rules like modus bonus and such. But here I'm just trying to go fast, and hopefully you'll have a cheat sheet in the exam. We had one, so hopefully it won't be very hard. But be sure, make sure that you're a professor. Okay, and so now this is simplified the most that it can be simplified. Just get rid of the parentheses because they are all ors, and you will have this. Now let's do the second one. That was P. So same thing, not P or not Q or S or R. We can get rid of the parentheses, not P or not Q or S or R. You see that these are the same, so they are equivalent. You can check here from the answer as well. Okay, so also I believe here in the answer they made a mistake. It should have been both nots, so not P or not Q, because when we have a not outside, it goes into both, not only into the first one. Also here it's very clear, it should be not P. Okay, negate the following statements. This is actually something that one might look over, this type of question. It also might come. Negate the following statements. So for every x, P of x implies Q of x. How can I negate this? Okay, so it's not for everyone that P of x, so it's not for every x that P of x implies Q of x. What does this mean when I say it's not for every x? It means that for some x, Q of x does not imply Q of x. So you could say this, and you could say something nicer. The really nice thing about these types of questions is that you can think logically. You can think logically, and you can find really nice solutions. So saying that some x, so it's okay. So first, if this was not clear, what is the opposite of saying that always this thing works? Is saying that there's sometimes that this doesn't work. Okay, if it's not always working, then sometimes it's not working. Just that's really simple. So and that's where this logic comes from. And when I say that for every x not p implies q, so for some x, if I say that for some x not p implies q, that also means that for some x I have q and not p. Because here I was saying that if p happened, q will happen. But here I will say no, some x, sometimes p happens. Okay, so sorry, I should have put the not here. P happens, but q doesn't. And here you see that they did the same as this one. Now the second one is really interesting, and here is where the things that I said about biconditional and XOR come to play. Okay, so let's look at this. So P XOR Q and P XOR Q and P if and only if Q. Okay, so I said before that these two are complete opposites. If this is true, then this is false, and the same holds, because if the XOR requires that one of them be true and the other be false. In other words, the XOR requires that they do not have the same truth value in order for the XOR to be true, while the if and only if requires the complete opposite. It requires that both of them have the same truth value. So when one of them is true, the other one's false, and vice versa. Okay, so what does this mean? This means that the negation of this entire thing, what is it? So the negation of P XOR Q is P if and only if Q, and same goes for P if and only if Q. Its negation is P XOR Q. So what will happen now is it will remain the exact same with one simple change. The AND becomes an OR. And here you can see that just the AND became an OR. Okay, so they made them both into XORs, which is really not necessary, because this is equivalent to this. But yeah. Okay. Now let's look at this one. So this one is saying that for every x, okay, so for every x I can find a y, or at least one y, that satisfies this. Its negation is what? Its negation is that for some x, what I can't find a value. One might think that its negation is that for some x, every value of y works. Actually, no. It's for some x, no value of y works. So yeah. So for some x, for every x, not. So for some x, no value of y works. And now for this one, if I finish my homework, then if my friends are available, then we will go to the movies. This one we have to negate in English. Okay, so first, not necessarily if there's an if in the sentence, then the negation will be an if also. That is because when you are trying to negate something, you are trying to say a sentence that is its opposite. So if I say that I need these conditions to be met such that I go to the movies, what sentence would be its opposite? It is that these conditions were met and I didn't go to the movies. So I finished my homework, my friends are available, and my friends are available. Friends are available, but we didn't go. And here they say the same. I finished my homework and my friends are available, but we didn't go. Now for the 8th question. Now very quick intro to contrapositive, converse, and inverse. Contrapositive, from its name, is positive. It is true if the original proposition was true. So if the original proposition was P implies Q, then the contrapositive would be if not Q, then not P. What does this mean? If P causes Q, then if Q didn't happen, of course P didn't happen, because if P happened, then Q. So this is the contrapositive. The converse is if the original one was P implies Q, then the converse is Q implies P, which is not necessarily true.
Because if if this was true and this was true, then it would be a biconditional, which is not necessarily true. Okay, so the inverse would be not P implies not Q, which is also not necessarily true, because if this was true also, it might have been a biconditional. Let's try and actually check if it would have become a biconditional, but logically I thought that. We take this and then we would get P or not Q, and this would be the same as Q implies P, yes, so if both of this would hold and this would hold, then it although and this would hold, then it would also be a biconditional. Why did I think that? It's because if not P, then not Q. So first, if P implies Q, then P causes Q. And if not P, then not Q, then the only thing that causes Q is P. So that would make it a biconditional, if and only if. Okay, so now, if you practice a lot, you will become a good programmer. What is the converse? The converse is, if you are a good programmer, then you have practiced a lot. The contrapositive is, if you are not a good programmer, you would have not practiced a lot, or you have not practiced a lot. Just basically, just think about this one. It's really easy, the first one. So this is P and this Q, and P implies Q. And just do the same as we did before. Now for the inverse, it's if you did not practice a lot, then you are not a good programmer. You are not a good programmer. You will not become a good programmer, maybe. Okay. So yes, these are the three. You can check if you are a good programmer, then you have practiced a lot. If you are not a good programmer, and then you didn't practice. And finally, if you don't practice, then you will not become a good programmer. Okay, so now, you cannot go out if you do not finish your homework. Okay, so same thing, going out if not finish your homework. So not homework implies not going out, right? So, first for the converse is if you, okay, so the converse is if you didn't go out, then you didn't finish your homework. The contrapositive is if you went out, then you finished your homework. If you went out, then you didn't finish, or then you finished. And then finally, the inverse is you can go out if you can go out if you finish. And here you can see that, okay, so you might think that the inverse, we said that the inverse is not necessarily true. But if someone comes and tell you you cannot go out if you do not finish your homework, what you would think is, okay, then if I finish my homework, I can go out. But that doesn't say that you can go out if you finish your homework. It just says that you can't if you don't. So there might be a case where you do finish your homework, but you can't go out. For each of these sentences, determine whether it's an inclusive or an exclusive or.
Startup is a company that was.
So now for each one of these, we have to see if it's an inclusive or an exclusive or. We know that this is the exclusive or and this is the inclusive or. What's the difference? Well, if you do the truth tables very quickly, you'd find that the exclusive or, there's one case that differs from the or, is the true. The exclusive or gives you a false because they need to have different truth values for the exclusive or to be true. Okay, so now to enter the country, you need a passport or a voter registration card. Okay, so this is clearly what? It's clearly an inclusive or, because if you had both, you'd definitely be able to enter the country. Okay, enrolling in CMPS 11 Math 1 is required. Okay, so now let's think about it. Maybe this was in the context of like registering for a course, and for registering in a different course, then this is the prerequisite. But okay, that doesn't really make any sense, because why it be or, especially that Math 1 and CMPS 11 have nothing basically in common. So let's think about this. Pause the video, think about it. Enrolling in CMPS 11 or Math 1 is required. This would be this could be understood in both ways, but I believe it's closer to being an inclusive or, yes, because you could be enrolled in both, but maybe like you were thinking about it in the context of someone, maybe his first semester in uni, then you could register for either one, because registering for both maybe would be a lot of workload. You could think about it like that. Actually, these types of questions are sometimes tricky in this manner, because it's really sometimes up to interpretation. But yeah, try to think about it logically and see what fits better. When you need it, you can't find it, or it's not available. Okay, so this is an exclusive or, I believe, because, okay, so let's say you need something and you didn't find it. You don't really know if it's available or not, I guess. Yeah, and if it's not available, then you know where it is, maybe. So I think that this is an exclusive or. Let's see. Yes, it's exclusive or. Dinner includes steak or chicken. I believe that this is exclusive, because like steak and chicken would be too much money to offer in one dinner. Maybe if it's a restaurant or something. So yeah, I believe it's exclusive. Okay. Okay, so now for exercise 10. P of x is someone being a CMPS major, Q of x is taking CMPS 200, which is now CMPS 201, and then you have to express these statements using quantifiers, logic and connectives, and their negations in English, and x is the people in CMPS 211 course. Okay, so it's you people, hopefully. Okay, all people in CMPS 211 class, which is everyone in our domain, are CMPS majors, so P of x is CMPS major, so for everyone here, they are CMPS majors. This one is pretty easy. What's its negation is someone in class is not CMPS. Again, if you wrote everyone in class and not CMPS, this is completely wrong, because the negation of this is not necessarily that everyone is not CMPS. It's at least someone is not CMPS. And then you would say the negation in English is someone in class is not CMPS major is okay. Some students CMPS are not CMPS, as we said. Okay, all CMPS students taking CMPS 11 are also taking CMPS 200. Okay, so yeah. Okay, so all students in taking CMPS 211 are taking CMPS 200. Let's see. Everyone, all CMPS students taking CMPS 211. Okay, so we know that for every x is everyone taking CMPS 211, but that doesn't include every CMPS student, so we have to say everyone in the CMPS 211 class that is a CMPS 211 student is also taking CMPS 200. QX CMPS 200, right? Yes. Okay. So if you are a CMPS student in the domain of CMPS 211 people, because that's our domain is CMPS 211 people, then that necessarily means that you are taking CMPS 200. Okay, so both of these work. Okay, so, and the negation of it, they didn't put the negation, but they asked us to do so, so we'll just do it. So what's the negation in English? Let's not even try to put it right now using quantifiers. But, okay, so what's the negation of all CMPS students taking CMPS 11 are also taking CMPS 200? Is that there's some students taking that is not taking both CMPS 11 and CMPS 200. Okay, and also here you'll notice that I didn't say there's someone that's taking CMPS 11 and not taking CMPS 200, because that's a specific case of the negation. Because if I would negate this, then what would I get? I get that for some x, not P of x and Q of x. So it's not P of x or not Q of x. So it's someone in the CMPS 211 that is not taking. Okay, So what does this basically mean? This basically means that someone in the CMPS 11 class is either not a CMPS major or not taking. Okay, so let's see. Okay, the truth. Okay, so these ones are pretty repetitive. You could do them on your own. If you want, you could go through the book exercises. I personally didn't. There are maybe some interesting questions that I was taught about back then, but there are basically too many questions. If you want, if you have the time, you could go through them. But yeah, that's it for our first session. Stay tuned for this next one, where we will be doing more challenging questions that will push you more towards the boundary and that will help you see if you are actually ready to take the CMPS 211 exam or not.